Okay, guys, so believe it or not, we're on our last hurrah here. We're in the fourth quarter, and we've got some talk about body defenses and some of the wily ways these bacteria get around our body defenses, okay? So the first thing I'd like to do with you guys is to make no assumptions. I know many of you actually had me in anatomy and physiology, second half, and I know you have immune system under your belt. Many of you that are not from SUNY Broome, but you're coming here to take a course in micro, I know you have bio background. So I'm going to go through the body defenses. If I go too quickly, you want to let me know somehow, get in touch with me if you have questions. But we're going to talk about all information that would be found in chapters 17 and 18. And let's go right into it here. So the immune system is a tough one because among systems, it's kind of functionally a system. There are cells all over the body. You can't just take one organ and like the heart and say this is the heart and this is what it does. I suppose you can pull a few immune system organs out, like the spleen, the thymus, structures like this. But you would also find immune cells in the bloodstream, in tissues, all over the place. So it's a functional system. And what we usually do to try to describe and understand this functional system is we talk about how it behaves, okay? What kinds of functional, things that these cells do. All right, so we talk about an innate or non-specific side of the body defenses. These are general defenses against a wide range of pathogens. This is the kind of thing that exists at birth, and it's rapid in that respect, could get faster, right? An example of something like this would be the skin. It's not the kind of body defense we think of when we talk about building immunity to things, okay? So this side is not something we build as we get exposed to things. This is something that's already there, built in. Okay, it's a built-in defense against a wide range of things. Versus adaptive or specific side of body defenses, this is what you're probably thinking of when you say, you're going to build an immunity to something. And this is a more narrow defense against specific pathogens. In fact, it's oftentimes against specific features of those pathogens. And this is we're going to require some kind of exposure. You need to be exposed to something specific about a pathogen, whether it be bacterial or viral or some other eukaryotic cell. And for that reason, it's a little slower. You have to work up your defenses against it. All right, so we're going to look first at this non-specific innate side. First of all, we have physical barriers like walls around a city. And I oftentimes think about this as kind of like, like Lord of the Rings kind of thing with a wall around the city. Literally, you have physical barriers to bad guys that are outside of us, right? So these pathogens are kept out by our skin, by the inside surfaces as well. So mucous membranes, we're talking about inside the nose, the mouth. If you voyage into any orifice on our body, okay, you're going to find mucous membranes. And some of these mucous membranes go clear on through us, right? Like the digestive tract has mucous membranes going from mouth to anus all the way through, all right? And anything that stays, that is kept out by those mucous membranes, technically never really enters our bloodstream. We also have aspects of inflammation, phagocytes, which are certain kinds of cellular barriers we're going to talk about, and fever. So let's first jump right into the physical barriers, talk about these a little bit. What are some of the features of physical barriers like the skin, the cutaneous membrane, right, that make it really good at protecting us? So one thing we can say is that this thick, keratinized, stratified squamous epithelium, this is a thick wall, right? Lots of layers to a wall. That's what we want in a protective wall. And it's strong. We have this keratin protein in there that makes these resilient barriers. This is a fairly dry surface. Okay, bacteria, they don't like growing on dry surfaces for the most part. There's a few exceptions, and we'll talk about them, but generally they don't like it dry. So this is going to bring down pathogen growth on our surfaces. Now, we do know some places on our skin where it can get a little more moisture, right? And those are places, generally, we have more problems with pathogen growth and bacterial growth in general. We also have oils that are going to be ejected out onto the skin by sebaceous glands. These are generally antimicrobial. We have flora that naturally live on these surfaces despite the fact that it's dry. And these organisms are always going to compete with pathogens. So our normal bacteria, our normal flora are really good things. And on top of being dry, there's salty and an acidic characteristic to our cutaneous surfaces. Just think about sweat, for example. You know, if you taste sweat, it gets in your mouth, it's going to be salty. And it's also got an acidic property to it most of the time. All right, so these are all great things that are giving protection to us from bacteria. Generally, they don't like it in these kinds of conditions. Now, this would be showing you an exception, right? So this is an image from our lab where we actually had some skin bacteria that would love to grow in salty environments like this mannitol salt plate, right? And some of them will even ferment for us versus over here where we see some bacteria that will grow in that salty environment, but it won't ferment certain things. All right, what about the mucous membranes? If we go into any of these systems, digestive, urinary, and so on, we're going to have not as strong a wall, but still a stratified squamous wall. Inside any of these openings, this is what we're going to find. And generally, we're going to find similar characteristics, some of the characteristics to what we saw on the skin. We're going to see lower pHs, like in the mouth. The vaginal mucous membranes are generally acidic. It varies depending on the stage of a female cycle, but generally acidic. And same with the urethra. In the stomach, that mucous membrane is really acidic, right? So we're going to see acidity again. We're going to see antimicrobial elements, not necessarily oils like you do in the skin, but you're going to see that the saliva has certain elements, certain components that are antimicrobial. Tears are going to have antimicrobial properties. And antibodies we'll find, okay? There's normal flora on all of these mucous membranes, and they compete. They help keep us healthy because they compete against pathogens. And we know when these normal flora are reduced that we do succumb to pathogens oftentimes through the use of antibiotics. Mucus, we're going to see mucus there. We're not going to see it on the skin, obviously, so that helps to trap particles. Cilia move those particles up away from certain sensitive mucous membranes, like in the respiratory tract. Here we see some cilia that would move that mucus the other way. And let's forge right on into what would happen if we broke through this wall. So we have this great characteristic to skin and mucous membranes in that it's just a physical barrier. So what if there was some kind of break in the wall, right? So this wall through the city, around the city, has a breach, right? I usually think of inflammation as a call for backup. What do we need to do when there's a hole in the wall and the enemies are coming in, right? So you have a cut on your skin, let's say. Generally, what we want to do is stop those invaders from coming in and spreading throughout the city, right, throughout our body. We want to fix the area. We want to, any of our own men, of our own protective security guards that are there, right, the army that we have, we want to move our dead cells out of the way. And we want to get rid of the pathogens. We want to prepare the tissue for repair, right? We want to seal that hole as quickly as possible. And a lot of times inflammation looks like this, right? It's red, it's swollen. There's a lot of pain there because pain receptors are being triggered and there's heat. Now, most of what you see here is due to the blood, right? If it's red, well, there's more blood there. There's more blood flowing into that region. So guess what? It's swollen, right? This does not have to be an open sore either, right? You can have redness and swelling from some kind of damage done on the inside underneath the skin. And heat. Generally, the blood is warmer than the surface of our body when we take somebody's temperature. So these are the general steps of inflammation. We have a breach in the wall. Here's a splinter through the skin, right? We want to make sure that we summon all the help we can get to this region. And that is the first step you see here. We have this set of inflammatory chemicals that are going to be released like a bell going off, right? There's a big gaping hole in the wall. We're going to have sirens going off. These sirens, a lot of them, these inflammatory chemicals, are making it so that the blood pauses in this region and brings more white blood cells in here, more troops to the region, right? And you can see here there's several steps to this. There's inflammatory chemicals like sirens going off, making something happen here. But then there's margination, diapedesis, chemotaxis, and phagocytosis. We're going to go through these steps now. Okay, these are all part of the inflammatory process, and remember, still part of non-specific. This is all in place. We don't need to have some kind of recognition of anything unique about the pathogens here. Okay. So, inflammatory chemicals. What many of these inflammatory chemicals being released in a location of damaged tissue is what they're going to do is vasodilate capillaries in that region. They're going to make capillaries wider, and they're also going to make the capillaries leakier. Okay, basically the sophisticated term would be there's more capillary permeability. More in the blood is able to seep out of that blood. Okay. What kind of chemicals are doing this? Histamine is doing it right off the bat. If there's any kind of damage like this or any kind of inflammation, histamine is oftentimes a real active player. And we know we put in antihistamines into the system, right, when we don't like the effects of inflammation. Prostaglandins are a later effect, usually in some inflammatory process. These increase pain, and of course we throw other drugs at that, like ibuprofens will affect prostaglandin. Leukotrienes also increase pain, but are an inflammatory chemical, and there are kinins as well. So this is a host of different inflammatory chemicals. And there's also other amplifiers of inflammation that are called complement that are part of this process. We won't talk about those nearly as much. All right, so what are the benefits of this, right? So we have this vasodilation, we have leakiness of these capillaries. So stuff from the blood that's always in the blood are going into this area. We don't think of this as a good thing because we always think of, oh, we have to bring down the inflammation, right? But what I always teach my A&P students is inflammation is a normal process, and it's the first step in the healing process. So without inflammation, you won't get to a healing mechanism, okay? So what are some good things about this? Hyperemia, more blood flow to a region, brings all the good things blood has to that region. Oxygen, nutritive value, right? Nutrients, and white blood cells. More troops are being called in. That's the call for backup. There's an exudate. There are clotting factors in our blood, and those clotting factors will seep out in this region and help us to throw a big fibrin net, a clot, right, over these cells. We don't want them to spread, right? That's the big thing we talked about a little earlier. Inflammation is a part of the process where you're going to kind of throw a net over these bacteria, and we're going to increase temperatures here. Those temperatures are going to help us to increase reaction time. There's a lot of reactions going on when we look at the inflammatory process, so a little bit of heat doesn't hurt, okay? It's when we have constant, sustained, high fevers that we worry. But warmth in a region, not a bad thing to get reaction times up. And usually pathogens enjoy our mesophile kinds of temperatures at 37 degrees. So if we crank it up above that, a lot of time pathogens are not very happy with that and with that change. Okay, finally, what is this inflammation going to bring about? Well, a lot of the white blood cells flowing through the capillaries in this region are going to start to stick to the walls of those capillaries. They're not going to zoom on by like they usually do. These white blood cells typically in healthy tissue are going to zoom right on by. But a lot of these inflammatory chemicals cause proteins to be produced on the inside endothelial cells of capillaries. And so like a golf ball rolling on the dew of an early grass in the morning, right? So it's going to really slow that golf ball down if it's rolling on wet grass. And that's what this is doing here. Margination, white blood cells are going to attach and slow down as they roll against the wall margins, right? The capillary margins. Diapedesis, these white blood cells will squeeze their way through the wall, and they will travel to the site of the damaged tissue. Chemotaxis. And we've talked about chemotaxis already, right? In this case, it's our own white blood cells that are using chemicals and they're moving towards that chemical. In this case, the chemicals are the inflammatory chemicals. All right, so a white blood cell is not going to just diffuse out every direction. It's going to move towards the site where the damage is done. And eventually, a lot of these cells are phagocytes. A good number of them are neutrophils, which are the most abundant white blood cell of the bloodstream. And they are generally phagocytes. They're going to be gobbling up some dead cells, pathogens, a whole mix of things. And ultimately, the collection of these white blood cells, dead cells in that region, and potentially pathogens that might be replicating, right, going through a division process there, these are what results in a pus formation. Okay? All right, we're going to leave it at that for now. We've got a good half of that non-specific done. We'll go into some of the phagocytes involved here and fever and be done with non-specific after the next clip. Okay?